Again, welcome to Physics 4B. Today is October 28th, and this is again, we're still basically finishing. Actually, there was an item that I didn't really finish on chapter 28. That's one thing. And then the other thing also is the lab. I promised to have the instructions available to you before today, and I did post it on campus actually yesterday. I still did not post the rubrics, but I guess you guys understand how the rubrics now work. Basically, the name is required, and you get a point for it. If you don't include it, you're going to miss a point for it. Both the objective and the conclusion are graded. There are some requirements for both of them. The objective is worth 3 points if you include at least two sentences describing exactly the goal of the lab. And because this lab is actually two labs at once, so it still counts as a single basically objective for both of them. But I hope that you guys make a distinction. And again, in the rubrics that I'm going to publish soon, because the lab I extended the due date for it, is that you need to clarify exactly what is the objective from the first activity and the second activity. There are two activities in this lab. The first one deals with the magnetic field, both for permanent magnets and also electromagnets. And the second portion of the lab deals with the second lab actually is DC motors, okay? So that is basically what this in terms of the labs are. They're posted there on Canvas, so hopefully you guys had a chance to go through them. I'm going to briefly talk about those instructions anyway, so we're going to go through that. And then also in terms to continue with the points of the rubric also is graded based on the questions. Every question is worth 2 points. You will get 2 points if you get all of the answer correct, using proper sentences. Don't give me those brief answers, basically yes or no. That's not acceptable. And also including data if it's asking for numbers, including units if it's asking for numbers, appended to the numbers, basically their units, and answer correctly. Now, if any of these components is missing, such as, for example, you include just the data and forget to include first sentence and description exactly what's going on. Some of the questions are lengthy questions. They have 2 to 3 parts in them, so they require all of these points to be answered to get the full credit. If you don't do that, then you'll get partial credit. If you miss a question or you don't answer it completely, then in this case you get 0 points. So those are in terms of basically the name, the objective. The conclusion also requires at least 3 sentences or more. Connect back to your answers with the data. In this specific lab, for example, what you're going to do is for the permanent magnet, all you're going to do is first of all locate, and I'm going to go through quickly with it, is go with there is a device there that measures the magnetic field in Gauss. So you're going to go near the magnet on the left hand side and take a reading immediately, making sure that the Y component of the magnetic field is reading 0. So you're going to read the X component, which will turn out to be actually the magnitude in absolute value, of course, of the magnetic field. So you're going to take that data, and then another one, about 5 data on one side of the magnet, and another 5 data on the other side of the magnet. Now you have a set of 10 data. You're going to plot basically this function. It's going to be from negative to positive, so it should pass by the origin if it's a linear function as a function of distance. The thing to remember about this distance is actually an arbitrary distance unit, so just numbered 1, 2, 3, 4, and it's actually they are equally spaced. Okay, so you can't just take any arbitrary points on the near the magnet. So that's basically answers that question. And then there was another question related to the magnetic field inside the bar magnet. So you have to take the meter and put it inside the bar magnet, basically. So this is a permanent magnet. Then what we do with the electromagnet, basically, in that case, you change the number, first of all, of turns in it, or loops, from 1 to 4. And at each time, you're going to locate the meter at specific location, read the magnetic field, again, making sure that the y component is 0 so that it's easy to compare the x component to the y component. You don't have to go to the Pythagorean theorem and find the magnitude of the entire magnetic field. Since one of them is 0, the other one you don't have to worry about it. Since we're just looking at the strength of the magnetic field, we don't even care about the sign. So at this point, you're going to take the reading for 1 turn, 2 turns, 3 turns, or 4 turns. They're called loops also. Okay, so now you have an idea of how the strength of the magnetic field should depend in terms of the number of turns. In another part of the activity where you're not going to be actually collecting data, but varying on your own the strength of the battery, which will mean the strength of the current that is going in the loops. You fix the number of the loops at that point, you don't have to change it, and you just change the value of the electromotive battery from 0 up to a certain value, whatever that value is, and you're going to tell me how is the strength of the magnetic field, again, changes with the current, okay? And that should be a question. That is a question. So in other words, these questions, they have multi-level types to them. Now, the data in the tables, they're all worth 1 point per entry cell, per cell. At some point, you're going to be drawing the magnetic field lines for permanent magnets of different shapes. So that is basically the part with the magnet. This is lab 1. This has to do with the magnetic field for both permanent magnets and also for electromagnets. The second part of the activity for the lab is going to deal with the DC motor. I gave you basically the materials that you will require. Again, this I discussed it. Do you guys hear me well? Because I changed cameras and microphones. Okay, very good. At least one person here is okay. The others have no opinion, I guess. Okay, very good. So I have more than one. So basically, you will need this one, the one I have here. I don't know, is this fuzzy? Camera is focusing on me. So instead of focusing on this thing. Okay, it's 28 gauge basically wire. Okay, as you can clearly see. This is the wire I'm using in here. Okay. In my demo, I used about 67 centimeters of wire. Okay. So this is the wire I used, about 65 to 67 centimeters of wire. I have actually four turns, and as you can see, I shaved it. I was going to do it with the sandpaper, but since I did not go outside at all to get sandpaper, what I use pliers actually to yank the cover from it, to yank the coating from it, because this is coated and it has to be coated. So you don't use another one that is not coated. Otherwise, if it's not coated, what happened in this case, there will be a short circuit in here. Okay, you don't want that. You want it to be coated, and the ones I sell them, they are already coated, so you don't have to worry about that. So I use the pliers, which I dropped somewhere. I mean, you should see this room. I mean, it's a mess. There are things all over the place. Anyway. So I use pliers similar to this ones, but this is actually cutters, okay? They are not pliers, okay? To strip this thing off, okay? To shave it. So that's basically and I need to do that. It's very important that you do that. So that is part 1. It asks, and you can go on eBay. Not eBay, I'm sorry. I don't use eBay anymore. You can go actually on Amazon, and you can buy I think they are $8, but they come in a set of 4. So you really don't need 4 of them unless you have other purposes. So what I have in here, I have a battery holder. Okay, so that's the thing that you do. Now, if you don't have access to a battery holder, you don't want to spend that much money because sometimes it's not really necessary to do that. So what I suggest you do is take a battery. This is a 1.5 battery. It's a D-cell battery, as you can clearly see from the label in here. The positive is on this side, the negative is on the other side. What you need to remember about it is that what you can do, actually, you can take this end and using a rubber band, You can tie the rubber band around the battery several times and it should work. I mean, this is a very short rubber band. I don't know how much I spent on this rubber band, but they have a bag of them, a whole thing of them from Walmart, actually. So anyway, and they should hold. They should work fine too, okay? They should hold your connection between the negative end where it's broad, but the positive end is kind of narrow. So you have to be very careful with the positive end on the other side with the anode. So what I suggest you could take a Play-Doh or something else and basically make sure that there is a connection in there. As long as there is connection and the battery is working, you're fine, okay? Okay, an old, what should we call it? Flashlight holder also might work. Okay, you might repurpose it if you don't use that flashlight, but you have to be careful with it so not to destroy everything. I have this thing in here, basically. I have to bring my magnet now, and you need a magnet. You need a permanent magnet for this purpose, okay? The magnet and the battery, they hold fine because there is metals in the battery, okay? Now this could hold it there. Now again, if you don't have access to, I have a bunch of magnets. Unfortunately, I was talking to the dean this morning and I was seeing if I can basically get my students to borrow my magnet. All of this are magnets, by the way, okay? And not only this, I have other magnets too, okay? But unfortunately, he said that it's too late for this semester, maybe next semester. So sorry, guys. Okay, so I have my connection in here, okay? I have my wire in here. This thing is not shaved all the way. So if it slips one way or the other, especially since I am holding it on one end, as you can clearly see, I did not shave it all the way, and that's a problem, okay? So it might slip to this side and cut the current. And if it cuts the current, this thing is not going to work. Not only that, but I need to make sure, and I'm trying to do a visual in here, that this is as close as possible without touching the magnetic field, okay? The magnet, I'm sorry. Okay. I hope that this is more or less lined up, okay? So it's connected from one end. I can feel it right now in my hands. Actually, this is fast. I can feel it in my hands right now, okay? You can see if I give it a, you need to give it some sort of a starting point in here, okay? No, it slipped. Oops, it fell off. Okay, I probably should do this on the computer, and maybe I can move the camera quickly. Okay. Okay, so you guys see it trying to go. Once it goes, it jumps off, okay? So there are some ways. First of all, I need to shave the whole thing, okay? And if I'm not holding the camera, I will probably, did you see it go, guys? Until it basically, so it did not last as much as I was hoping it does. So if you're going to do this, you're going to record. So it's trying, you guys remember mu equal to, the torque is equal to mu cross B. Okay, it went for several times until this arm, as you can clearly see, actually has moved. So if you're going to do this, make sure you shave it properly so that this arm, why is it focusing differently in here? Until this end actually moved, the unshaved area moved to the point that basically, let me stop the camera quickly so that I move it because it's going to make you guys dizzy. I position it correctly. Okay, so this is basically, it moved for me because I really did not shave it correctly, but I hope you guys will fix it so that it doesn't do that, so that this thing will work. Now it's working. Okay, until this end comes back again, okay? So that's the trouble I'm running into. Oops, now it flew completely. Okay, so I hope you guys have an idea of how this thing is going to work. Now, you have two options. Either you build your motor, okay, and you share it with us via recording, and I want to make sure that it's you who did it and not your uncle or your somebody that you know did it for you. So I want to see that you're doing it step by step. So you're going to record the whole thing step by step on how you built your own motor, okay? And I will see your face there too, okay? That way you're good, you're fine. Now, other than that, what you're going to do is I'm going to send you data and you're going to do calculations and you're going to answer those calculations short of doing this. So I'm going to send you actually the data that I have for the types of materials that I have, and you're going to calculate the torques, you're going to calculate basically the energies associated with it, and basically find the strength of this motor and how long it's going to last for you and things like that, okay? So that is basically what the second part of the lab is that has to do with the motor. You're going to tell me actually in the lab report whether or not you're going to do one or the other, okay? Does this make sense to you guys? At least the demo. I'm going to go into the details of the lab. This is again trying to recover from last Monday because I did not share with you guys the file. Okay, so let me go back into the lab report itself, the lab report form. I know I posted it on Canvas, so I hope you guys have had a chance to look at it. So labs, and it's the magnetic field lab, and it's the battery report. Okay, and let me go back to the beginning. And let's go back into here. Share. Where is the PDF file that I just opened? This looks like it's a Word file. That's not it. Oh, here it is. Okay. Again, you're looking at the lab report form for you guys for this two lab. No, that's not it. Sorry, looks like it, but that's not it. Okay, so what happened in here? Where is it? Yeah, it's this file. Okay, so let's go back in here and let's share file. And here it is. Good. So this is your lab report form. Again, it's similar to another class that I have. Actually, they have different settings, so it looks like it. They have different. Actually, it's part of another assignment for them. Again, this is basically the stuff that I was talking about in terms of grading, so don't forget that. There is a question immediately that has to do with the monopoles, okay? And I hope that you guys understand the answer to this question, okay? And what happens to the monopoles, okay? Single electric charge exists, known as a monopole charge, but does it exist also for magnets? So basically, I hope that you know how to answer that question. Now, the objective is in here. There is nothing in here, so you don't have to worry about this one. So again, try to leave the objective until the end, till toward the end when you're done with the lab, basically, then you have an idea of what you just did so that you can basically put it together. Or you can read through it and you will have an idea and then come back and state your objective, okay? This part of the lab in here, all you're doing is drawing the magnetic field, and the instructions in here, it tells you to label the following permanent magnets and draw their magnetic fields. So in this case, if I label this one as north, okay, this is north, the other side is south, the magnetic field will always point from north to south, okay? But on the other side, it's going to curve around. So that's one. Now, cylindrical magnet, this is a magnet that looks like it's a cylinder actually, and I don't have one in here that is cylindrical shape, but it looks like a bar magnet like this one, but it's a cylindrical, okay? It's a cylinder again. So what happened in this case, this is a circle, this is a circle, the entire side is basically drawn like this. So the magnetic field will go again, where is the north in here? That's the north. It's going to go from the north all the way, come back to the south, okay? And then from the bottom, it's going to be the other side too, okay? So this is one. Now on the surface itself is going to look like it's emanating, it's coming out of the screen in here, okay? And leaving it from this side. So it's this side should be, if this is the north again, the lines should be coming out, which is like dots. And from this side is going to be like X's going out, okay? Now if I have two permanent magnets and I line them up, so assume that this is basically the magnets that I have. This is not the case, okay? This is actually a horseshoe magnet. So if I line them up, depending on the sides, they will either repel or attract. And this side in here, I'm lining them up so that the north and the south are facing one another. So if this were the south, this is the north. So the field lines will go from the north to the south, okay? Now I line them up in here differently, okay? So that the north and the north are facing on the opposite side and the south and the south. So the field line should be now like going like this. Where is my pen? And tools, comments. Let me take the drawing pen. So technically in here, they should be something like this. Okay, the two magnets are repelling one another. In this case, again, they're repelling one another, so the magnetic field will be trying to end up in here, okay? But in this side, they will not cross to one another. So basically, there should not be a cross. I crossed them just right now. And this side in here is going to go like this. Coming from north to south, okay? So this is opposite to that because now I have them in opposite directions. Now a disc magnet, this is one of them, okay? I have the positive one, the north on one side, I have the south on the other side. So the field lines again, they will come from the north and going to the south, okay? And from the center also, the opposite, in the opposite direction. So from the center, they will be in this direction, going through the hole this way. From this side, they will be emanating this way, okay? So in other words, if this is counterclockwise, this is going to be actually clockwise, okay? Now, if I have two magnets, one of them, the field lines actually, they will again emanate this way, okay? Okay, so they're leaving from here and they're coming in here. Again, it's not, you have to draw this ones as best as you can. If you can do it electronically, fine. You can do it by hand and scan the documents. Now, in this case, they're repelling, so they're trying to leave and here trying to leave, but they cannot really end up on the other side. So in here, they're repelling one another. Okay. So that is basically in a nutshell the first part in here. Then we're going to go into the permanent magnet. So the first one was actually drawing the magnetic fields. The second one is a permanent magnet. You have to click on this link. So I'm going to click on it. And once it comes in, I'm going to stop sharing that screen. You may need Java installed on your computer, not JavaScript. JavaScript should be by default on your computer, okay? But Java itself. So it's the loading. It's loaded. Okay, there are two tabs in here. There is the bar magnet and there is the electromagnet. So we're going to take the bar magnet. So the first thing you have to do is bring this intensity to around 80, okay? 80 is good enough, okay? And move the magnet so that its center is more or less lined up with one of these compasses, the small compasses, and then make sure the compass itself is straight. It is straight now. And make sure the end in here on one side or the other is actually touching one of them so that you have an idea of how the strength of the magnetic field. We're not going to need this compass. Actually, we can probably remove it. I know I left it on, so we may need to remove it. And then you're going to take show magnetic field strength. So what you're going to do in this case is there is the total magnetic field. There is the X component for the magnetic field. There is the Y component for the magnetic field. And there is the angle in which the magnetic field is oriented, which direction is pointing. And it follows the red basically part of the compass. So if I bring it in here, okay, right, in this point, watch the value of by. I need by to be 0. So right now it's negative. That means I'm above. So I need by to be 0. So I need to bring it up a little. I wish there is a way to control it. Can I do it by mouse? No, you can't control it by the mouse. You have to do it by, I mean, by the cursor. You have to do it by the mouse. The point I'm trying to say in here is make sure the y component is 0. It doesn't, the point, if I stick with this point, it's going to be a problem for me. It's going to be a big error, okay? Because if I move it to the other side, I really need to stick to the same value of the by. In other words, I need to stay in the same x-axis, okay, throughout. So that's why the x value is 0. The y value is 0 will put me right on the x-axis. That means I'm only dealing with, man, it's very difficult. That's your task, guys. Seems like I can probably move also the bar magnets a little. Well, that's your job, guys. You have to be patient with it, which I am not right now because I'm doing this session too. Okay, here's the deal. If the value of by need to be to stay the same, okay? What I need to record in my table now, let me go back and stop sharing the screen quickly here and share with you the lab report itself. What I need to do is come to this table and record this value as -1. So how much is the strength of the magnetic field according to my data? Share. It's telling me 79.67. Okay, but I need to stick with this negative value. That's the problem in here, okay? So you have to stick with the same value. So I have -0.2. So this value that I'm going to go into my data, I'm going to put it in 79.65. Now I'm going to move it to position 1, away from it, and make sure I have the same value for, wow, I almost got it 0 here, but I don't want to do 0 now because I moved it to. So probably this is close enough. So this is the -1 now, -2, I'm sorry, okay? It's 12.83. As I move away from this bar magnet, of course, the magnetic field starts to weaken. Now, I'm going to go to a third one. Probably, yeah, almost there. This is good enough, okay? 4.18 for position 3. So let me show you where this 12 and 4 need to go. So I'm going to go back into my PDF file. So the first one was 79. The second one was 12, and the third one now is, how much was it? 4 or something like that? 4.18. So I need 2 more, okay? So I need the value for 4. Which is, again, I need to bring this by to about -0.2. Okay, that's good enough. So it's 1.76, okay? For 1.76, that's going to be the fourth value, which is the second from the top. And then finally, the last value in here. Seems like I'm moving further away. Is 1.09, okay? So that is 5 values. So it starts with the fifth one, which is the furthest one, and then you bring it down closer and closer toward where the magnetic field is, where it's super strong. Okay. Now let's do the positive values. So I count 1, 2, 3, 4, 5. So let's start from the fifth one, which is 0. So this is the BY is very small right now, 0.79, and then bring it to 1.57 as I get closer. Then bring it to a value of 3.38. It's increasing as I get closer. Okay, and then for the position 2, now it's going to be 8.68, and then for position 1, it's 42.71. Okay, let me stop sharing the screen and go back to my data file. So here is the thing. This should be the smallest of the negative values, which are on the left. And as I move closer and closer, the magnetic field should be stronger and stronger. This should be the strongest magnetic field. Okay. Then the same thing in here. The weakest will be around the fifth, basically, compass. And as I move closer and closer to the magnet, it's going to be stronger and stronger. What are these units? They don't have any number in here. It's arbitrary units, so don't put any units for them. The magnetic field is given by this meter in Gauss. Remember 1 Gauss? 1 Tesla is 10,000 Gauss. So this is when you say 100 Gauss, you're not looking at super strong magnetic field then, compared to basically the huge values of 1 Tesla, 2 Tesla, which are sometimes produced in the lab. Sometimes in the lab, we can even end up with 30 or 40 Teslas, which is super strong magnetic field. Okay, so that's why conveniently we use the Gauss, because if I'm using Teslas, what is the difference between 80 Gauss or 0.0008 and 0.000793? It looks like the same thing. Okay, but 80 Gauss or 81 Gauss versus 75 Gauss, it looks like it's a big difference, a big gap of about 6 Gauss or 7 Gauss. Okay, so that's the unit for the, and you can leave the Gauss in here, it's fine. Okay, it's 10,000 times smaller than what the Tesla is, which is typical thing. Then we're going to answer in here. We're going to basically, at some point, we're going to graph that function. Don't put the origin in here, because if you put the origin in here, you will have the negative values. Where are you going to put them? So we're going to put the origin somewhere in the middle of the graph, and you plot them. Okay, because you're going to have positive values and negative values for the position next to the magnet. And what happened to the magnetic field inside the bar magnet? So all you have to do now is take your meter in here and put it right in the magnet in various location and read the magnetic field. And you're going to tell me what's going on with the strength of the magnetic field inside the bar magnet. So you need to answer that question. So I know in the data collection we're skipping the inside of the bar magnet itself, but outside we're not skipping it anymore. Okay. Now, let's continue with the, stop share this file and go back into the lab instructions. Come on. You're going to graph this. If you do an Excel file, please include it with your lab report. Okay. Based on a graph, how is this thing depends on the magnetic field. So we're going to see a line or we're going to see something else. Please describe the strength of the magnetic field. Is this line going this way? Is this line going that way? It's up to you to determine exactly what's going on. Okay. Of course, the magnetic field now looks, since we're looking at its strength, the line should be above the positive axis. So you can put the origin in here because that's a positive value. We don't care about the direction. Okay. So the entire thing should be above the x-axis, above the in the positive direction of the y-axis. So that's, but you're going to tell me the strength, how it depends, how I move away from it. Now, if I do the electromagnet, it's the same thing. So I'm going to stop sharing the screen, go back to where we were earlier, and change to an electromagnet. Now, once I change to the electromagnet, I'm going to change the number of turns. As I said before, I know I left this thing in here on, but you can remove it. Actually, you don't need it. And here, to show the electrons, just to give me an idea of how strong is the electric field, electric current right now running. So again, I'm going to show the field meter. I'm going to bring it to about, actually, I should start with 4 to know roughly where I'm going to put the meter. So I'm going to put it somewhere in here. Okay. And again, try to have the BY equals to 0. It's perfect. I think I'm going to quit now. I did good job. Okay, the BY is 0 right now, and the angle is 0, so we're in great shape. Okay, so leave it there. So I'm going to go back into loops. The number of loops is 1, and I'm going to read the strength of the magnetic field. Now it's 21.42. Add another loop to it, and now the magnetic field is 42.84. Now add a third loop, it's 64.26 Gauss. Add a fourth loop, and now the reading is 85.68. All of this data I needed for my leave it as is. Don't change it. Don't change anything in terms of the meter itself. Okay. So you go back in here. So stop sharing the screen. Go back into my PDF file. So this is what I was talking about. Record that data in here. Okay. Now, based on your data, how does the magnetic field strength depends on the number of loops or the number of turns. Okay. So we're going to answer this question in here. And for 4 loops, vary the strength of the battery. And notice how the strength of the magnetic field changes with the voltage in the battery and the speed of the electrons in the circuit, namely the current, because the speed is actually the current. Okay. How do you think the magnetic field depend on the current? What values of the voltage in the battery would give you a 0 Gauss magnetic field? Again, all you have to do now is, let me stop sharing the screen, go back into the activity itself. Is this thing in here? Change the value and see the reading on the magnetic field. What happened to it? Is it getting stronger with weaker and weaker batteries? And are the electrons moving faster and faster at this point once you increase that? You can clearly see that the current changes also accordingly. Okay, so up to a point where I should have no motion. That means I cut the current because there is no battery in here, 0 volts. Okay, what is the strength of the magnetic field in that case? So that is basically in a nutshell. Let me stop sharing the screen. Go back into the lab report. So this is part should be fine, and you guys have an understanding now of how an electromagnet works and how permanent magnet works. In this case, again, you're going to go and see how motors are made, see how we basically got this one going, get a D-cell battery, all of these materials. At this point, you're going to tell me that you prefer to build or you're going to prefer to calculate. If you want to calculate, then I'm going to send you the data, and I'm going to tell you in detail about what needs to be done in order to really write the report, because it's going to require you about almost 2 pages of basically calculations and also answering questions and things like that. Does this make sense in terms of the 2 labs that we have before us? Okay, Daniel thinks it makes sense. Now, is Daniel alone? What do you mean by years? I know it's a typo. I'm just trying to pick on it. Okay. Okay. Okay, thank you, Sebastian. Okay, very good. So this is basically in a nutshell in terms of the lab. Now, there was another item that we were supposed to discuss at the end, and I did not really discuss it, and because we were running short of time, and when you run short of time, you really, I do, at least personally, I make a very lousy job at it. So, okay. Inside magnets, inside materials, this is solid state physics, actually, not really this kind of physics, is that, of course, we have atoms that makes up basically the different materials, especially if we're talking about metals in here. And those atoms, what is my nice magnet, the one I was doing for the motor? Where's the actual motor? Oh, here it is. Okay. This is a permanent magnet, okay? So it's not electrical or anything like that. So this is called the ferromagnet because it retains its magnetism, because right now it acts, and this is the one I used earlier for magnetic, for the motor. So again, I bring a material in here, put it next to it, and it's all of a sudden it attracts it to it. So this material, on the other hand, is called the paramagnet. What's going on in a paramagnet is the following. This is iron. It can be magnetized, as a matter of fact. If I put it long enough with this one, it could be, should have about a magnetic field. Now this is the needle that we use again to basically try to understand the magnetic field. Right now, it's not magnetized. Had it gotten a magnetic field, it would have responded to it. This, on the other hand, probably, okay, it did not. Okay, it's not responding to it. It did. Yeah, it's responding to it a little bit. Okay, but it's only short-lived. Okay, so a paramagnet, like iron, for example, which plays both, is the following. Basically, what you have inside the atoms, the iron is kind of a bad example, actually. It's not a good idea. But other metals, what you have in this case is that you have the electrons going in their orbits around the atoms. So this really requires quantum mechanics, physics 4C, that 4D, that is. Okay? And as they move, think of the electron as if it's a charge, because once in a while it's going to go, every t period is going to go around the atom, basically. This is a classical model. This is a very bad picture, okay? It won't work really in quantum mechanics. So if the electron is moving around the atom, it's as if a current is flowing in the opposite direction, because the electron actually is a negative charge. So when the negative charge moves in one way, the current will flow in the opposite direction. So there is a current now that is flowing in that direction. Since they have a current now, and it can actually find the current value, which is just the charge divided by the radius in this case, divided by the time in this case. It takes to go once, so that's charge divided by time. It gives me the current. So that's the rate at which the current is flowing actually around each atom. And the period t is actually related to the velocity of the charge divided by what is it? It's the period is the 2 pi r divided by v. Okay, the velocity of the electron. So in this case, I can express it in terms of the radius of the atom itself, which is of the order of an angstrom, and also the velocity of the electrons as they go around the atom. Now, since I really don't have a velocity, and basically in quantum mechanics, the velocity is one of the problems that you need to deal with. So I really need to convert that into angular momentum, because with angular momentum, I can work with this one. The angular momentum for a mass from physics 4A, if you guys remember, is just the mass times the velocity. That's the linear momentum times the radius, okay? So that is my basically expression here in terms of angular momentum. So I have the entire thing now expressed in terms of angular momentum, and I have now the current. All I have to do is just multiply it by the area A, and the area is just pi r squared, and now I have the magnetic moment created by a charge going around the atom. So think of every electron going once around the atom is actually a magnetic, it has a mu in itself, okay? In addition to that, quantum mechanics introduces another thing, which is called the spin, and that is not a classical concept at all. Think of it as the electron going around its axis, basically spinning, okay? But that's not an accurate 100% picture, but that is nonetheless, in addition to the orbital angular momentum, there is actually another linear momentum that the electron has. So the combination of these two motions will give me a mu, which is the intrinsic mu for every single electron going around the nucleus, since you have a bunch of them and they all move in different directions. First of all, in every single orbital orbital location where there are two electrons, their spins actually cancel. This is due to Pauli principle, so that one of them is positive, the other one is negative, so that at the end, actually those two, they contribute none. So at the end, the free electrons, now we have a problem with them, but on average, due to thermal agitation, they don't have any kind of magnetic moment, okay? In the presence now of a magnetic field, what happened? Mu cross B of each one of those free ones start to align itself more or less with the applied magnetic field. Although the thermal agitation will make some to deviate a little, but on average, this thing becomes more and more stronger. And at the end, what we have actually an induced magnetic field in the material due to the presence of an external magnetic field. This is equivalent, if you wish, to the induced charge in the dielectric, okay? So this is similar to that. And in this case, the permeability of the medium can be altered, just like, for example, the permittivity of the medium was altered in the dielectric, in this case in magnetic materials, to represent how much the value has been changed from mu naught to a different value of mu. And from here, we have now, we have this situation now. The thing with it that is different than the permittivity is the permeability can be either positive or negative. It is positive for paramagnetic materials, and it's negative actually for diamagnetic materials. And that, in a sense, so if you apply a magnetic field, some materials actually repel to it, not attracted to it. They repel actually because they induce the opposite direction. Others are introduced in the same direction and they're attracted to it. Now with ferromagnets, what's going on, the case of nickel, cobalt, and iron, they have something called the self-consistent solution. You know what's going on. Let me explain this a little bit with the, let me share with you my, so what you have in here in each region, not specifically each atom now, we're talking about regions of atoms. So you have this atom, for example, let me get a drawing tool in here. You have this atom, for example, the outer electron, for example, is moving in this direction. You have the next atom next to it, the outer electron is moving in this direction. You have this atom, the next electron is moving in the same direction. So now they are helping one another to move in the same direction. And this atom is moving in this direction, and this atom is moving in the same direction. All of them, this is a region now, it's called domain. So all of this now, electrons, they're moving in this direction, okay? Obviously, the electron in this region is going this way and the electron going in that way, so they cancel. The currents in here actually cancel one another. The same thing in here. This current is flowing in this direction, counterclockwise, but this one in here, it's also counterclockwise, but they're opposite to one another. So where they join, they cancel. But on the outside, this electron is going this way, and it's the other one also going that way, and this one is going this way. So this entire domain seems to have a current flowing in the same direction, counterclockwise. This entire domain now will have a magnetic field that is given by the right-hand rule. It's coming out of the screen. So there is a B now, a net B for this region that has a magnetic field actually pointing out. Okay? Now think of this, because they're randomly distributed in the material, there are different regions. Let's say, for example, this is pointing up, this region is pointing this way, this region, because again, thermal agitation, this one is going that way. So different regions, I'm trying to draw them on the screen. This region is going this way, yet this region, for example, is going that way, and so on and so forth. On average, they cancel one another. Now, if you bring an external magnetic field, they may add up to a net magnetic field in here, okay? So it's still, for example, I'm going to take about 4 or 5 regions, 4 or 5 domains. So this domain is this way, this domain is that way, this domain probably is this way. But as you can clearly see, there is a net, actually, magnetic field pointing more or less in this direction, okay? So in this case, I have, when I remove the magnetic field, the external magnetic field, they retain their magnetism. They lean on each other in what is called the self-consistent solution. So the materials now, they stay with one another, okay? Leaned up. So now, not all of them, of course, line up, depending on the external magnetic field. If it's very strong, then they become more, most of them actually line up until almost all of them line up. And there is a maximum because you only have a certain number of them. You can't have more than what you have of domains. So it's going to saturate. Okay. Obviously, if you apply the magnetic field in the opposite direction, you're going to start to change them in opposite direction until the saturation happen in the opposite direction. So this is how this looks like. I'm going to have the B applied. This is the applied magnetic field. This is the B induced. Actually, it's called the magnetization. So if I apply the magnetic field and keep on increasing it, the magnetization or the magnetic field inside starts to get stronger, stronger, and until I reach a point where it saturates. So this is the saturation. I cannot get any more aligned because I have most of them, 99.9999% of them. So all I'm adding is just that extra percent, trying to add it to the picture. Now, if I apply the magnetic field, it does not follow these lines. It's going to come to the certain points until I cancel all of them. So there is no more magnetic field inside. And then it's going to be reversed. Actually, they will be applied now. in the opposite direction until I reach the saturation. Actually, I reached it too soon in here. I'm sorry. So it's probably the saturation will be reached down the road, okay? Here. Which is the same value, by the way, but in the opposite direction. So now I'm applying negative magnetic fields in the opposite direction, basically. That's what that means. Now, if I apply, if I reverse the magnetic field, the applied magnetic field, now I'm going to cancel this, and the curve will not actually follow the original one. And I'm always going to describe this curve. This is called the hysteresis. Hysteresis. I don't know if I spelled it correctly or not. Hysteresis curve is this one. And it's actually, there is a memory, if you wish, of how the process went from the last time. And this is actually the essence of the old hard drives. Not SSDs. SSDs use the different technology. So I can store information, actually, if I apply a strong enough magnetic field in magnets, in materials, and that is actually what the old hard drives they are. Actually, there are disks in them that you apply magnetic field to them different directions, and they will create this different regions with specific mapping. And now, if I bring the needle that is going to read it, and if I go around it, it's going to induce currents in it, and those currents actually going to be read, okay, to give me either a value of 1 or a value of 0 for the data I have stored in my hard drives. So this is basically the old magnetic materials that are used to store data, old hard drives, okay? Old hard drive technology, I should say. Okay? Magnetic devices to store data. So this is the part of chapter 28. So it's a fascinating topic, actually. This is solid state physics. When you're dealing with these things, you're dealing with material science, and you have to have an understanding. And again, I just barely describe things in terms of classical mechanics. These things really, in order to be fully described correctly, they have to really have quantum mechanics involved, because these things involve atoms and motions and things like that. So this closes the book on chapter 28. Again, this stuff is not testable stuff in terms of this class for X4B, but just to complete the picture, if you ever were asked to what causes the magnetic field in a permanent magnet, believe it or not, it's currents. So there is a current in here, just like an electromagnet. And this current is through this self-consistent solution, okay? So that is exactly what it is. So if somebody asks you, you're walking in the street and somebody stops you and says, hey, what is a permanent magnet? You should be able to give him or her that answer before you walk away. Did anybody encounter a person like this one? Come on, guys. Did you meet somebody in the street who said you've never met in your life? Asks you what is a permanent magnet? Come on, guys. Did you or did you not? I know I don't have the entire class. Okay, Sebastian at least was. No? Okay. I assume the rest of you always meet this person in the street who asks you what is a permanent magnet. Because it seems like only Sebastian was not lucky enough to meet that person. How about you guys? Bao, Eric, Alex, and everybody else. Okay, Daniel also. Seems like there are two unlucky guys in here. Okay, whether or not you're lucky enough to meet that person or not, this is the discussion of the day, is what is a permanent magnet? What causes a permanent magnet? Okay? And I just answered it. I assume that I am that strange person that you meet in the street. I have some weird covering things on my head that if you see it, you probably would not recognize me if we meet in the street. And I will ask you, okay, so what in the world is a permanent magnet? Okay, so you should give me that brief answer. What causes magnetism in a permanent magnet? I can understand an electromagnet. As we saw earlier in the lab, if you change the current, I can actually kill the entire magnet. So there will be no magnet in an electromagnet. And that is how actually we achieve tremendous amounts of magnetic field is through an electromagnet. In the industry, we use electromagnets. We don't use permanent magnets. We use permanent magnets, for example, for making small values of the currents and things like that, but not the big values. Okay. The big values, usually in lab and things like that, they're reserved to electromagnets. So it can kill the current and there is no more magnet. So I have an understanding of that is change it, increase it, the current is doubling, the magnetic field is doubling, okay? So there is no problem with it. But what is going on in the permanent magnet? That is the question of the day, and I just answered it just to give you clear another overview of it before we close the chapter 28, I'm sorry. Is this idea. So this is what causes the permanent magnet in this case. It's this domains, regions in a material where the current is flowing consistently in the same direction. The net current, there is no current actually in there. The electrons, as they move, as if they are producing an electric current moving in the same direction. Each electron is moving inside its own atom, okay? But overall, they seem to create that region of space. So we have domains, and these domains, they align themselves more or less in the same direction. And if I apply an external field to them, they retain their magnetism by leaning on one another. Does this make sense to you guys? Okay. Sebastian at least is good with it. So since you never met this person, so now you're ready, Sebastian, for him or her. Good? The others, they seem that they have already dealt with that person. Okay, so hopefully that will be in the discussion and you guys will remember that. Now, we're going to jump into chapter 29 now. Unless you guys have questions related to either the lab or chapter 28. 28, I already did an example from the book on Monday during the lab session. Okay, so we're going to jump into chapter 29 now. Okay, so chapter 29, let me go into the topics for it, deals with the following. The experimental evidence that a changing magnetic field induces an EMF. An EMF is an electromotor force, basically a battery. Okay, force that pushes the electrons around the circuit, around the loop. Okay, so that is something. Okay, again, how Faraday's law relates the induced EMF in a loop to the change in the magnetic flux through the loop. Okay, so we have to define what that magnetic flux is. Again, similar to how we define the electric flux, we're going to define the magnetic flux. In industry, the magnetic flux is far more important than the electric flux. Okay. So we usually deal with this one. It has its own unit. It's the Weber. So that's to tell you how important it is. Okay. In the case of the electric field, the flux of the electric field is just the unit for the flux for the electric field, which are volt per meter times the area, which is meter squared, or volt times meter. And here they gave it actually a unit because of its importance after Mr. Weber. Now, how to determine the direction of the EMF? It turns out this is the trickiest part of the whole thing, the direction. As a matter of fact, if you were going to go probably to graduate school or upper division stuff for physics, you're going to be dealing with this sign a lot because this is really what determines things. And this plays a major role in the industry because the sign itself it has applications, for example, for magnetic levitations, for trains, for example, in Japan or other places. They use it a lot. So this is important. Now, it turns out for this entire chapter 29, and this is the recommendation that everybody goes about it, and same thing true in here too, is there are two stages in solving these problems. The first stage is find the value of the EMF. Ignore the sign for a moment, okay? Find the numerical value for the EMF, how many volts there is, okay? Once you find the value of the EMF, then, which turn out to be most of the time the easy part of the problem, is the value of the EMF. Then look into the sign issue, okay? Because the sign issue, it's not going to be an obvious thing. So you really have to find. In other words, is this EMF pushing the current? For example, if I am looking at it on the plane, is it pushing it counterclockwise or clockwise? That is the trickiest part of the whole thing, okay? So once you master that skill, you're in good shape. Then you don't worry about this entire chapter. So this is the key. Portion of the 29.3 is a key for understanding the rest of the stuff on how to do calculations and things like that. Because it matters a lot, okay? Imagine I have a circuit. And I have a battery with a given EMF, for example, 46 volt battery. And I take the entire circuit and dump it into a magnetic field and move the wire in or out, okay? Or take the magnet and move it in and out. Now the magnet, since it's moving in a location, we will see, according to Mr. Faraday, will create its own EMF. If it's changing, if its flux is changing. Since its flux is changing, it's going to create an EMF, then I need to know, is it helping my 46 volt battery or is it in the opposite direction? So the numbers in your answer will matter a lot. So instead of finding, for example, current of 2.43 amps, it might be just 2.1 amps because of the fact that you took the wrong sign for the EMF that is induced by the changing flux of the magnetic field. And this could have severe consequences down the road, because you could have a different value for the current, so you could have estimated different value, for example, for your electrical components, and the whole thing can go south on you because, for example, the current probably is too strong or too weak for your components, and it can either burn them or overwhelm them, so something can go wrong on you. So the sign issue will be critical. So understanding it is going to be critical. And you will see in the statement of Faraday's law, with the correction of the sign that is named after Mr. Lenz, actually, is a big mouthful. And the whole mouthful has to do with the sign itself, nothing with the Faraday's law itself. I can tell you what Faraday's law is. I mean, Faraday's law states that basically the EMF induced by, in absolute value, if you wish, I don't care about the sign, has to do with the rate at which the flux of the magnetic field changes with time, okay? It's equal to actually to the rate at which the flux of the magnetic field is changing with time. So this is the first part of the law. The second part of the law, when Mr. Lenz came in, he said that this EMF is actually equal to minus d phi of the flux of the magnetic field with respect to time. Because he added the minus sign and he added the rule of finding it, this law now became known as Faraday-Lenz law. Okay. Okay, so once we have that, then we're going to deal with the rest of the chapters. The rest of this chapter, how changing flux generates circulating magnetic. Again, I told you guys last time when we talked about this one, the EMF actually is the force or the energy needed. It's not a force, okay? I know the word force is inside the EMF. The EMF, again, stands for electromotor or electromotive force. It's not a force in newtons, it's actually in volts, okay, which is joules per coulomb. So it's basically how much is needed for a charge to move through a whole circle, a whole cycle, a whole loop. So that's why I need to do an integration over a closed path, okay, of E, which is the force times the displacement. I mean, per unit charge, this force. This is coulomb per, this is a Newton per meter. Remember, the force is QE. So this is the electrostatic force times DL. That's a displacement. This is the total energy in joules. But since I'm doing it per unit charge, I drop the Q there, okay? And it's going to just be the product of the electric field times DL. So this is what actually we mean by the EMF. In other words, this battery that I was doing the experiments with it already, where is the numerical? This is a 1.5 volt, okay? Where is the thing in here? This is a 1.5 volt battery. There's another one I have in here. That's a 9 volt battery. That means that if I have 1 coulomb running from the negative to the positive, that 1 coulomb, this battery will take 9 joules from it on 1 coulomb. 9 joules, that is. Obviously, if I have less than 1 coulomb, it's going to be less than 9 joules. So this is the one that you go to the store and tell them, I want a 9-volt battery. So what you're telling them, I want an energy of 9 joules for every coulomb. Okay. When you connect it to a special location, you might not drain the entire 1 coulomb. You may drain just a fraction of it. That's why you don't drain the entire 9 joules. You drain a fraction of it. Same thing. This is a 1.5 volt or 1.5 joules for 1 coulomb. Okay. And actually the unit for it has to do with the joule per coulomb. That's exactly what the volt is. Okay. So this is the EMF that is, we've been talking about it all along. It's actually the work done for 1 coulomb, the work in joules for 1 coulomb. Now, having said that, this electric field, which is the EMF is expressed in these terms of this relationship, will have a very, very, very weird thing. Okay? Let me check this notification quickly here. Okay, so we'll have will not be actually a normal electric field. How are we doing on time? Still have a good thing here. Good. So will not be actually a field that is going to be diverging. It's going to be a field that is going to be actually more of a field that is going to circulate. So this is in a nutshell what we'll be describing. So we're going to find this electric field. Okay. And that electric field will be different than an electrostatic field, okay? And then from there, we're going to discuss the eddies and the rest of the chapter. So let's delve into the chapter unless you guys have any questions. So again, like I said in the beginning, so we still have about, I'd say probably about 15 minutes maybe. Okay, so we need to get some stuff done in here before we close these things on it. So, again, I need to, the need for it was basically that Mr. Faraday and other people in his time, they were actually interested in one idea. And the idea was the following. When Mr. Ampere basically came up with his law at the end, remember Ampere's law says that the circulation of the magnetic, what is it? The circulation of the, I'm trying to remember how we put it together. Yeah, of the magnetic field over a path in this case, okay, is equal to mu naught I. So in other words, if I have a current, I'm going to get a magnetic field. So this is Ampere's law. This is from chapter 28. Okay. So what this thing is saying then is that if I have an electric current, I have a magnetic field. And we demoed it. Actually, I demoed it for you guys. If you have a current, you should be able to, that's what the idea of the electromagnet is actually too. That's part of the lab too. So in an electromagnet, you turn on the current, that creates a magnetic field, period. End of the story, okay? Current running through a wire will create a circulating magnetic field. So the magnetic field is actually due to electrical currents. So we understand that part. Now, what causes a current to begin with? In a wire, for example, a conducting wire, what we have in this case is this is a bunch of charges that are ready to move, okay? Remember, that's what the current is. That's what the conductor is. So the minute you apply a difference in potential, delta V in here, between these two ends, what happened in this case, the charges will move. So the charges will move. In this case, let's say, for example, this is at a higher potential. This is at a lower potential. Charges will move in this direction, actually. In actuality, the electrons are actually moving in the opposite direction, but that's between you and I, okay? So in this case, we're going to connect it to a battery of some sort. Did I draw it backward? Yeah, the current is flowing this way. So the charges will move in this direction. This is high and that's low. They have to always fall. Okay? The charges will fall from high to low. Okay? So it doesn't matter. Anyway, the charges are moving this way at this point due to this battery, which is what we call an EMF actually too. Okay? So what's going on in this case, I have actually applied an electric field because this is V high, this is V low, so this is with which the direction of the electric field is pointing. Since this is the direction of the electric field, then I can say that the electric field is the one that causes the current to begin with, and that's true. Because what causes the charges to move to begin with is due to this force, the electrostatic force in this case, okay? So what causes the electric field, the electric current was the electric field. So in this case, people, they knew that the electric field is actually the one responsible for the magnetic field. So that's what we knew then. So that's another topic of the day too, okay? So Ampere's law basically can be stated as the electric field creates a magnetic field. Period. Okay? So that is basically what Ampere's law is. So that is item 2 of the discussion today, in addition to the first question that has to do with what are the permanent magnets. Now, people in that time, they were trying to speculate, especially Faraday and other people also. Could the other way around be true too? Could the magnetic field create an electric field? So that's what the question that they wanted to understand. Okay, so in order for that, they were experimenting with the different magnetic fields and see what's going on. It turns out not the electric field that creates, not the magnetic field that creates. So experimentally, it was shown that the changing magnetic field creates, I'm going to say currents, because that's what it's going to do directly. In other words, electric field, because we know current is actually must be due to some sort of an electric field of some sort. Okay, so that is what the experiment has shown. And this is the expression I was talking about earlier. So this is equivalent to basically a battery, because this current exists now with no battery. So as if I have a battery, as if we have a battery with an EMF, okay? So when they were doing that, they wanted to find the value of the EMF, and immediately Mr. Faraday stated, and there were some other people also who did that, that it's actually the rate at which the flux of the magnetic field changes with time. So this is the value of the EMF, okay? So it's the rate at which the flux of the magnetic field changes with time. So we need to define what that flux is. Again, we did that. Magnetic field, the flux of the magnetic field. The rate of at which the magnetic field flux, the flux of the magnetic field changes with time. Okay, when we defined the flux of the electric field, if you guys recall that, we said, now, since we were using the letter phi for the flux, now we're going to embellish that one with the letter E for the electric field. It was defined in general as the sum of the product of the electric field over an area of calculation. So this is any area. Okay, we'll do. Gauss's law, if you guys remember, it says that over a closed area, the flux of the electric field was equal to the charge enclosed over epsilon naught. But that is special case. That area has to be closed, okay, for Gauss's law. Now we're going to do the same thing for the magnetic field. And we're going to discover immediately a law similar to Gauss's law for the magnetic field. So I'm going to define now the flux of the magnetic field. And I put the letter B in underneath just to make it different from this one. It's just the sum over the dot product of B times dA. Okay? Now again, this is over any area. It doesn't have to be closed. It can be anything you like. Now, if I'm interested trying to find what is the flux of the magnetic field over closed area, I'm going to immediately say it's 0. This is closed area. And why is that? Because similar to this idea in here, where we count the charge enclosed, here we really should count the poles enclosed. How many poles enclosed? And since the magnets come always in pairs of poles, north and south, so either I am not enclosing any poles whatsoever, I have no magnets at all, or I have them in such a way that the magnetic field will leave the positive north pole and come to the negative south pole in such a way that they loop around, so that at the end I count no more, because at the end there is a cancellation. So this result is due immediately to the fact that we don't have monopoles, no monopoles. So that's easy. If I'm interested in the version of Gauss's law for the case of magnets, I know what the result is. I don't have to do any calculation, because again, all I'm counting is how many poles are enclosed in that area. Since the area is closed, I should not enclose any. If they do exist, they exist in pairs, so they cancel. If they don't exist, that means I don't have any magnets whatsoever, then I don't have any. So in either case, the total is 0. So both of them just should give me 0 magnetic field in this situation, okay? Does this make sense to you guys? At least this last result, okay? Which brings me to the third point of the discussion today, the fact that the flux of the magnetic field over any, and I emphasize any here, closed area is 0, because there are no monopoles. So we had quite a few questions today, monopoles, okay? So now, how about this one? Open areas. Now, open area can have a flux, okay? Open area, the reason why you can have a flux is because you can point towards it a magnet, and then, so this is an area, for example, that is not closed. So this area, for example, is sitting in space. Think of it, for example, this thing bag in here, okay? It's open from one end, albeit it's closed from the other side, it's fine, okay? As long as I can bring now a magnet like this, okay, and put next to it, so there is field lines that are coming from this side and they never come back to it, okay? Now, if, on the other hand, this area is closed, the field line that comes in must exit from the other side, so they cancel. The field line that is coming from this side must exit from the other side, and they cancel. But in this situation, where I have it open, okay, if I put a magnet in here, the field line will penetrate. There is no area in here that through which it's going to cross. It's basically going to go through empty space and then come out. So I only have field lines coming out in this situation, okay? So this example in here illustrates the fact that when the area is open, the field lines, even for a permanent magnet or a magnet in general, it doesn't have to be permanent or not, then might be a finite value. The field lines will come, penetrate it, and go through the other side. The field line will come and penetrate it through the other side, and the same thing So in this case, of course, this line probably is not going to cross it, but there are more lines that are going to come through it and so on and so forth, okay? And at some point, these lines probably, they will never come to it, okay? Because by the time they come in here, they're going to probably come across this way. So there is definitely a net value. Yes, some of them will come probably cross it, and they will come back in here and cancel some of these field lines. But there is definitely a value in here that is of interest that I'm going to have, as long as this area is open. If the area is closed somehow, whether it encloses a magnet or not, if it encloses a magnet, the field lines that leave it will ultimately come back to meet the other side, where the permanent magnet is, or where the magnet is. If the magnet is outside, as the field line go in, it must come from the other, somewhere else from the other area. So at the end, I count 0 net field lines in it, therefore I have no magnets, okay? So this hopefully illustrates the point. So an open area could have a magnetic field, okay? So this is basically what we mean by the flux of a magnetic field. From now on, the flux of the magnetic field or anything else will have actually this phi b in it for the magnetic field and phi e for the electric field, okay? Just to make that distinction. And the units for the flux of the magnetic field are easy. So the units for the magnetic flux are supposed to be the units for the magnetic field, which is a Tesla, by the way, times the units of the area, and the units for the area are the meter squared. Again, we don't call them Tesla meter squared, we use the Weber, okay? So this is the unit for the flux of the magnetic field, okay? We still have about 3 more minutes, and I think it's good enough for right now to stop. So basically the point being, in here we have 3 questions now today. Hopefully you guys caught them. And we will meet on Monday. We will finish this chapter hopefully on Monday, okay? And then we will have an application from this chapter, and we should be ready for the exam. And the exam is going to be a week after this coming Monday. And the exam will cover chapters 27, 28, and 29. Okay, any questions before we stop recording? No, I did not update the mastering physics questions yet, but I expect to have them soon because I'm having difficulty actually with them. I don't like a lot of the questions themselves too. So I still did not completely give up on it completely. So I'm still hoping to have that. Now, in terms of the exam, it is very important that you do the actual problems from the three different chapters, all of the homework problems. That's very important. So do not take them lightly at all. Okay, so if you expect to do this part correctly. Now, as I mentioned before, this part of the exam usually is not as easy as the second part. So I expect you guys, you take this stuff seriously and you prepare for your exam seriously so that you come ready for it. Okay. Now, I also did a problem from chapter 27 in class, and we did also a problem from toward the end. So this is not a small example, okay, the ones that we sometimes do. This is something big from toward the end of the chapter. And I also did a problem from chapter 28. We did that on Monday during the lab session, okay? So I expect you guys to go through those ones also. They are part of your preparation for the exam. So they are free game as far as the exam is concerned. There will be also another problem from toward the end of the chapter from chapter 29. So I expect that also to be included. So you have quite a few materials to prepare. So I don't think that, honestly, at this point, because there are no new assignments for these chapters in mastering physics. So at this point, we should not worry about that part, at least in here. So focus only on these problems. Thank you, Sebastian. Anybody else has any other question? Well, if you guys don't have any other question, I'm going to stop the recording. The lab is due not this Saturday, the Saturday after, okay? And again, I need an answer in terms of what you want to do with the motor, okay? Okay, see you guys on Monday then. So let me stop the recording.